Welcome to Lesson 13, Learn C Programming on the Raspberry Pi. Well, last day we did some pretty interesting things dealing with LEDs on the Pi, and I also introduced you to how to use arrays in the C language. So today we're going to continue on with that. First, we will go over to our Raspberry Pi and we will start up Genie, our editor. Okay, so you can see that what we did last day was I introduced you to the idea of an array. Here we have color, which is an array of 10 characters. And each of those characters can be accessed using an index. So, and the indexes in C start at 0. So color 0 is the first character, color 1 is the second character, color 2 is the third, and so on. Anyway, we're not going to use the LEDs for today's lesson. Instead, I'd like to go over a little more details on how arrays work. So let's make a new program here. And I'll just create a simple array here. Let's say an array of integers. I'll just call this X, and I will have, for example, 10 integers in that array. In fact, even on this declaration, I can also do initialization. So I can initialize the array to these numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have an array of integers. The array has 10 integers in it. Okay, so what we'll do is we'll just make a loop to print out those integers. So let me make a control variable, I, for my loop, for I equals 0, I is less than 10, I plus plus, and I'll say printf, and I'll say the value of x bracket %d close bracket is %d slash n quote comma. So you notice in my printf I have two formats here. Both are for integers. So the first one, I'm going to put the value of I. So I. And so this I, this value which goes from 0 to 9, will be placed in here. And then the second format string here, %d, will be used to contain the value of the array. So that will be x bracket I. Now let's see. It's a small short program. Let me save this as I'll save this as, let's see, in lesson 13, I'll save it as a1.c, or array1.c. So let's take a look at this code, what we have here. Move that over. What I have here is I have a variable called x, and that variable is an array because of the square brackets here, and it's an array of size 10. In other words, that array holds 10 integer numbers. So the first one I've initialized to a 0, the second one in the array I've initialized to 1, and the 10th one I've initialized to 9. And then all I do is I put a for loop here to print out those values. Okay, so let's see if we can do that. So I have it here. Notice I'm not using the wiring pi library, I'm not using the math library, I'm just using the standard C library. So just as a reminder, I could have added in minus LC to specify that I want to use the C library, but that's optional. I don't have to because the C library is always included. So I'll leave that off. Okay, so it's compiled okay, and I can actually run it. And you can see the value of x at 0 is 0. The value of x at 1 is 1. The value of x at 2 is 2, and all the way down to the value of x at 9 is 9. You notice the way we pronounce this, we say, in English we say x at 3 is 3, for example. So we use at in English to express the index value. So the indexes here, the indexes are 0 all the way down to 9 are the indexes. But the values are also 0 to 9. So let's change the values. Instead of having them to be 0 to 9, let's make the values, let's say 1 comma 3 comma 5 comma 7 comma 9 comma, oops, say 9 comma 11 comma 13 comma 15 comma 17 19. How many is that we have? 1 2 3 4 5 6 7 8 9 10. One too many. Okay, so if I save this guy and now I recompile my program and I run it, you notice how the values, oh, I think I missed one. Did I have 9 here? 1 2 3 4 5 6. Yes, I should have had a 19 in there to make 10. Let's do that again. So you notice anyway, you notice the last one is set to 0. You can't count on that though. You should always initialize your arrays before you use them. So let's compile this guy again and I'll run it, and now you can see that the value of x at 0 is 1. The value of x at 1 is 3. The value of x at 2 is 5. Okay? The one thing about arrays is that all the values in the array must be the same type. In other words, I can't put in here, for example, 3.4 because that's no longer an integer, that's a float. So everything in an array must be of the same type. Well, let's try making a float array instead. So I'll still call it X, but this time I'll say they're all float numbers. So I'll just put in, for example, 0.0, 3.0, 5.0, 7.0, 9.0, 11.0, 13.0, oops, 15.0, 17.0, and 19.0. So now when I print them out, I can't use %d for the value, I'll use %f. The index is still an integer. I is the index to the array. Then the index is still an integer. I'll put that here. I is the index to the array. So I can save this guy. We'll try compiling him now. And we got no errors. And I can run it, and you can see that x at 0 is a float 1. X at 1 is a float 3. Okay. And x at 9 is a float 19. Now, if I wanted to change one of these values, I could have. For example, in here I could say x bracket, let's say 0, 1. X bracket 1 equals, let's say, 22.2. So I'm really changing this value here from its initial value of 3. So I'm changing this. Remember, this first one is x at 0. The second one is x at 1. So x at 1, I'm changing to 22.2. So now I can recompile this guy. And I can run it, and you see x at 1 is 22.2. Don't worry about this little 1 at the very end. The reason for that is because computers just can't store numbers to infinite precision. Like, you can't have a number like 1.9537828, and it just goes on and on and on for infinity, because there's not enough RAM. So you get these kind of anomalies, these well, let's just leave it at that for now. But we'll get to it probably in a later lesson. Okay. So that's a float array. We can also have a character array, an array of characters. So, for example, char, and this time I would put in a bunch of characters. If I want to initialize, I have to put, remember, single characters are in single quotes. So A quote, comma quote, B quote, comma quote, C quote, comma quote, D quote, comma quote, E quote, comma quote, quote, comma quote, G quote, comma quote, H quote, comma quote, I quote, comma quote, and J quote. So here I have a character array of A with values A through J. So let me take this one out here, this line out here. And now if I want to print these characters, I have to say, instead of %f, I have to say %c. So I want to print out the characters one at a time. Okay, so I'll save this guy, recompile them, and you can see that now x at 0 is the letter A, x at 1 is the letter B, x at 2 is the letter C, and so on. Okay. Now if I wanted to, I could print this out, because this is an array of characters, I could print it out as a string by changing this C to an S. But if that's the case, then my string, I would just say, well, the value of X is, and I would just say print it out as a string as X, like this. So I could just print it out as a string. Now this may be problematic because strings in C should be terminated by a null byte or a 0 byte at the end of the string. But let's just see for fun what happens here if we try this. I'll save it. I'll recompile and I will run it. Oh, since we have a loop, since we have the for loop here, we're printing it out a whole bunch of times. So but you can see we're printing it out as a string. Okay, but you have to be careful here because C does require the last character to be a null byte if you want to use strings. So there's a subtle difference there between a string and an array of characters. Because an array of characters is just an array of a bunch of characters, whereas a string is like an array of characters, but it comes with the last byte must be a 0 byte, a null byte. So if we wanted to do this properly, first of all, let's take this out. We don't want to print the thing 10 times. I'll take all of this out and I'll just simplify it right down to to that. So if we're treating this X now as a single commodity, we're not dealing with individual elements. We're dealing with a single commodity called X, which is a string. Then we have to ensure that the last byte has a 0 in it. So let's increase this guy to 11 and let's put in the last position here, quote, \0, quote. And that \0, that's just a C way of saying it's a null byte. In other words, it's a byte, one byte with all zeros in it. I know it's a little bit, looks a little bit strange, but we'll get used to it. You'll get used to it. Let's save this guy. We'll compile him again. And then we'll execute it. And you can see the value of X is that. See, the interesting thing is if we would have put the null byte, let's say where the H was, let's put the null byte there, /0, quote. So now when we print out our string, it's going to print A, B, C, D, E, F, G. Because printing strings are defined as a bunch of characters terminated by a null byte. So let's see what happens here. We'll compile, and now we will execute. And you see it stops at G because we put in a null byte here, so our string stops at G. On the other hand, if I wanted to treat this guy as an array of characters instead of as a string, I could go back to the other way by using an index, and I could put a for loop. Now this time I is less than 11, I plus plus, and I could now print the value of X bracket %B D, the value of x at I, is %C. I'm going to print one character at a time. So here I'll say I, and I will say x bracket I. So this is the way we had it before, and I'll do that. So now I have an array here of 11, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 characters in that array. If I want to print out all the 11 characters, the indexes, by the way, are 0 through 10. So now I can print that out. Let me put an extra square bracket here to make it look nice. Okay, so I'll save that guy, compile it, and run it. And you can see now the value of x at 0 is an A, the value of x at 1 is a B, but if you look at x at 7, the value is null, nothing. That's x at 7. And then x at 8 is a I, x at 9 is a J, but x at 10 is another null byte. We have another null byte here. So if I treat the array in my print statement here, if I treat it as just an array of characters, then I can access all the characters. But if I treat it as a string, I can only access up to the null byte. Well, I hope that makes sense. Okay, let's try one more example here. Let me create a new program here. And I'll call this one A2. And I'll say, let's put in some, let's put an array here. I'll call the array Y bracket 10. And again, instead of initializing it, I will use a for loop to set the values of Y at runtime. For bracket I equals 0. I is less than 10, I plus plus, and this time I'm going to say Y bracket I is equal to let's say well, what could we say? You know what I'll do here, just to make sure I don't run into trouble, I'll say Y bracket, Y square bracket 0 is equal to 0. I'll just initialize the first value to 0. And then I'll do this one from 1. So Y at 1 is equal to Y square bracket I minus 1. Let's say times 2. It's a little bit tricky, but let's just see what happens here. Oh, actually we should do a printout too. Let's save this guy as, save it as A2 in lesson 13. Okay, and after that loop, so this loop is used to set the values of Y during runtime, and we will now do for, say I equals 0, I is less than 10, I plus plus, and we'll say printf quote the value of y square bracket %d square bracket is %d slash n quote comma I comma y bracket I. Okay, so in the previous example, right on this line, we initialized the values of y. But now we're going to initialize the values of y during program execution. So we have this for loop here, and the for loop is going 1 to 9. So it's only going well, 1 to 9 is 9 times. So y at 1 is equal to y at 0 times 2. So y at 0, well, let's make it plus 2. That times is going to get us into trouble. Plus 2. So y at 0 is a 0. Y at 1 is going to be a 2. Y at 2 should be a 4. Then a 6 and an 8 and a 10 and so on. Well, let's see if we can save this guy. We'll compile them. And we'll run it A2. So you see the values here. Y at 0 is 0, y at 1 is 2, and so on, because I did them during the execution of the program, during runtime here. So instead of initializing them up here at declaration time, when I declare. Okay. Now there's one more thing I want to show you before I end this particular lesson, and that is if we look at the addresses in RAM of where these values are stored. So let me do another printf here at the end of the loop. The address of y is %p slash n quote comma y. See, all I'm doing now is I'm just printing out the value of y as an address. The value of y as an address. So I'm saying a pointer. %p is a pointer. Okay, so I save this guy. Let's compile it again. And I can run it. And you see the address of y is 0x blah blah blah. Well, actually the 0x says that's a hexadecimal number, and that represents in RAM where the beginning of the array. So I could have put in here y is the start address. Y is the start address of the array. Just move that guy back here like that. So y is the start address of the array, and the start address is this. Well, let's try one more thing here. Oops. Printf quote address of y bracket 0 is %p slash n quote comma, and then I'll say the address of y bracket 0. So the second print here is I'm saying the address of Y0. Here I'm saying the address of the array. So the Y is the start address of the array. What is the address of Y at 0, of the first element? The very first element, which is 0 up here. What is the value of that address? Well, we use the ampersand here, say the address of. So let's take a look and see what we get here. We'll run it again. And lo and behold, you'll see that both of these addresses are the same. In other words, and this is kind of just semantics, but it's important, Y by itself represents the address of the beginning of the array. And the address of Y0 is also the address of the beginning of the array, but we usually don't say that. We usually say it's the address of Y at 0. Admittedly, they're the same address. And I know you're not familiar yet with hexadecimal, which is base 16, but let me show you, just before we finish this lesson, I'll show you a really powerful tool we can use in Linux called BC, which is the, oh, I don't have it on this system. Let me add it on. Sudo git install BC. Let me see if I can install it. Hopefully it won't take too long. It's not that many bytes. A little bit of patience required here. Anyway, while we're waiting for this, BC is an arbitrary precision calculator. It's usually available on all Linuxes. And before I run that, let's run our program again, just so we can get those addresses. So you can see these are the addresses here of where the beginning of the array is, but those addresses are in hexadecimal. So if I go BC and I say ibase, input base equals 16, and then I can type in this. I don't know if I think I might need to put it in uppercase. We'll see. Yeah, I think I need to put it in uppercase. BE 85321C. Then that is the address in base 10. It's a big number. Boom. It's 3,196,400,156. That is the starting address. 3 billion. It's a big address. Anyway, just to show you, the way you finish BC is you do Control D. So I'll hit the Control D character, and I'm out of BC. If you want to just play with BC, you can do things like this. You can say, for example, 2 to the power of 10. It says that's 1K. 2 to the power of 20. That's 1 meg. 2 to the power of 30. That's 1 gig. 2 to the power of 40 is 1 tera, and 2 to the power of 50 is 1 peta. In fact, with BC, you can go to town. 2 to the power of, I don't know, something like that. Of course, I don't know if the Raspberry Pi can do it. I guess that's too big for the Raspberry Pi to compute. Yeah, let me stop that. Of course, now I've hung it up. Yeah, let's try again. BC, let's just take a big number, for example, times where is it? Times some big number times big number, and you can see the answer comes out right away. So, you know, just multiplying two numbers in BC is very easy. When you're finished with BC, you can just say Control D to escape out of it. Okay, anyway, that's just an aside, just another command to learn in Linux, BC command. But just take a minute here to go over this idea of an array. What did we learn? Well, we learned that an array can be basically as long as you want. Arrays are accessed by an index integer, or individual elements of the array are accessed by integers. The address of the array is the same as the address of the first element in the array. We also learned that all of the elements in the array must be of the same type. So either they're all a bunch of characters, or they're all a bunch of floats, or they're all a bunch of ints, but they all have to be of the same kind. You can't mix them up. Okay. Next day, we're going to talk about two-dimensional arrays in C, because what I'd like to do for the next lesson, or maybe the lesson after, is to program the tic-tac-toe game or the noughts and crosses game. So we'll get to that at a later date. Right now, this is enough for lesson 13, so I'll see you for lesson 14.